All right, hello everyone. This is Trevor. Evelyn and I are going to be talking about a couple classification models that we put together to classify tumors taken from breast cancer patients. A little bit of background. So most people know breast cancer, very prevalent disease affecting about 3.8 million people at any time, largely women, but a few men mixed in there as well. Additional diagnoses around 276,000 annually. So that's like pretty extensive. Still killing around 40,000 people every year. So obviously it can be very deadly. And then this is in addition to an enormous economic burden. American Cancer Society estimates around $180 billion in lost economic productivity. And it's a lifetime economic burden for the people diagnosed. The treatment is very expensive. And of course, there's a huge emotional toll to getting a cancer diagnosis. And so kind of the primary question when a tumor is found is whether or not that tumor is benign, meaning it's not likely to spread and relatively treatable, or if it's malignant, which means that it is likely to spread to other parts of the body and could be very dangerous. Diagnosis, it's very hard. There are wide variance in the sizes and types of tumors that can be found, but from a broad level, this is kind of the process. As you see, there's multiple steps. The tissue biopsy step is especially prone to errors, and a number of studies have shown that error rates can be as high as like 30% in some clinics, but generally speaking, it seems like a more realistic estimate of misdiagnosis rate is between 8 and 12% of cases. These are both bad, both in the positive case where you're telling someone that they've got malignant cancer when they don't. So it's going to lead to overly aggressive treatment, which is dangerous in and of itself. And that's financially and emotionally and physically destabilizing. And then in the false negative case where you're classifying a malignant tumor as benign, you're allowing a potentially fatal cancer to go untreated. And so that's going to cause more aggressive treatment when it is found. But in either case, you're looking at increased probability of harm and or death. So these are things that we obviously want to mitigate and avoid. So Evelyn and I tested out a couple classifiers. These were built on data taken from the University of Wisconsin. So basically it's a set of tissue biopsy data that it comes in the form of basically quantitative attributes taken from these biopsy scans. So these are things like the radius, the shape, the smoothness, the size of the cells in the biopsy tissue. And then each attribute basically is given 3 measurements. So that's like the mean. So this is the average size of the cell, for example, the worst, so the largest cell there, and then the standard error of each measurement. And so data set 569 samples, it's pretty decent sample size for what we're trying to do here, and it's relatively balanced. So did not take a lot of work for us to use this and implement a couple models. Quick EDA exploration reveals that there are clear differences across different attributes between the malignant samples, which are the blue violins, versus the benign orange violins. And then looking at a couple in depth, you'll see that the density plots reveal, in this case, like a very distinct distributions in the worst measurement of the cell area. So you'll see the malignant cases there's a lot more variance and tend to be bigger than in the benign case. And then in some attributes, they're pretty much indistinguishable. This is texture, so basically looking at like what does the outside of the cell look like? Is it bumpy? Does it have a lot of proteins on it? That sort of thing. But so we're predicting this is not going to be very useful in our machine learning model. So the 2 that we went with, logistic regression, random forests, we went with these because they're known to be robust, highly performing, and most importantly is they allow for some analysis of the features involved. So basically, how important are features relative to one another, and how are the predictions actually being made. This is really important in the medical field because AI tools or machine learning tools that are not explainable are very unlikely to be uptaken by physicians who, generally speaking, do not like ambiguity. So I'll give you a little bit of rundown of the logistic regression model. Long story short, it does really well. But the first thing that we had to do was kind of narrow down what the set of features that we're going to use in the model. So I used what's called recursive feature elimination. This is basically a greedy backward selection algorithm. It starts with the full set of 32 features and incrementally removes one based on the performance added by that feature. So the least performing feature gets removed, and so on and so forth. And you'll see that, relatively only marginal gains after around like 5 features, but the optimal set that we found included 18. And so the important features, so there's 18 is obviously a lot of features. Most of those had relatively small coefficients, but the two that had really high coefficients were the mean radius measurement and the worst concavity measurement. So basically the average size of the cells in the tissue, and then the least or the most concave shape of the cell. So obviously to us, this doesn't necessarily mean a whole lot, but to clinicians, it's good for them to know what features are really being looked at in the model. How did it do on our test set? Very well. 6 misclassifications, which of course are bad in the case of cancer diagnoses. But it's important to note that this isn't meant to be a standalone tool that's just diagnosing patients on its own. It's meant to be a clinical support tool. So this is meant to kind of reduce the 8 to 12% misclassification rate seen by doctors alone. And so the logistic regression model obviously seems capable of doing that. Looking at the area under the curve, very high value. And again, we're not looking specifically at detection or specificity because both false positives and false negatives are equally costly. So now I'll hand it off to Evelyn to talk about the random forest.
Hi everyone, I'm Evelyn, and I'll introduce the next pages to you. Now we're trying to use random forest algorithm to build a model. All the features are selected in the random forest model, and the accuracy and F1 score is high, so the model works well. The ROC curves looks good. It means that this model can perform a high true positive rate while having low false positive rates. Then we go to the part of feature importance and analysis. First, let's look at feature importance ranking, using feature importance in random forest model. As is shown, the worst features are the most important. The perimeter worst, concave points worst, radius worst are the most important features. Second, most standard deviation features are useless. Third, most mean features are less important than worst features. Next, let's take a look at feature importance summary plot. We use Sharp package to print the summary plot. For each feature, the contribution to 2 groups is slightly different. Top features contribute more in malignant group than benign group. Now, let's take a look at the result visualization. For this part, we use Sharp package in this part. So for a specific case, the contribution of each feature is as shown below. As is shown, the perimeter worst contributes most, and concave points worst contribution is ranked second. The value of these 2 features supports that the diagnosis is malignant. However, the texture worst contribution is also high, and its value supports that the diagnosis is benign. At last, this case is predicted as malignant, which is accurate. This method tells us that how much a feature contributes in a case, and which kind of results the feature supports. It will definitely help doctors to diagnose in reality. This figure is interactive, and we are able to see the contribution of features and the prediction case by case. Now, we are seeing cases ordered by similarity. Put the mouse on the graph, and we can see a case and the features contribution on it. And now we are seeing case ordered by output value. This can help doctor grasp the diagnosed model in general. We then develop a simple model for diagnosis. The top 3 features in the previous random forest model are selected. They are radius worst, perimeter worst, and concave points worst. As is shown, the accuracy and F1 score are very close to the previous random forest model with all features. So it's an simple and good enough for diagnosis. What we can conclude in our work. First is that with views used for models both for research and diagnosis, we can use the comprehensive model to do some research and use the simple model with 3 features to do the diagnosis for patients. Secondly, with previous concerns about overtreatment, which might have a bad effect on the patient. We're concerned that the doctor might determine a tumor to be malignant based on worse features, but in fact, it is a benign, which leads to overtreatment. Through modeling, we found that the worst features are indeed an effective indicator that needs attention, and the false positive rate is very low. So the possibility of overtreatment is very small. Third, the ROC curve looks well. We can have high true positive rate while having low false positive rates. So there's no need to trade off, and the model will work well. So what we'll do in the future, we can generate some more data of more patients to improve our model. Also, we can consider more features about the patient, like their age or gender, and improve our model. That's all. Thank you for listening.